Welcome to Optical Sensors. So we can use optical fibers to make a chemical sensor called an optode. But before we can talk about optodes, let's review the refraction of light. So the speed of light in a medium with a refractive index of n is equal to c over n, where c is the speed of light in a vacuum. And this means that the refractive index for a vacuum is 1. So the frequency of light does not change as the light moves from one medium to another. But because the speed of light in the new medium changes, assuming that the refractive index is changing, then the wavelength in that new medium is different than it was in the old medium. And so note here that lambda nu is equal to c over n, where n is the index of refraction. So if we're looking at light in a vacuum, then n is 1, and we have c equals lambda nu, just like we've learned before. But if our speed is no longer the same, and the refractive index is different, then that means that if the frequency is not changing, the wavelength must be changing. Now, when light is reflected, the reflection angle equals the incident angle as measured from the normal. So we have a normal line here, that's the red line, normal to our plane mirror surface. We have our light coming in, and the angle between our normal and the incident ray is equal then to the angle between the normal and our reflected ray. Now, when light moves from one medium to another, its path is bent. And this bending is called refraction. And you can observe refraction with a straw in a glass. So you can see the straw is going in, and it appears to us, as we look through the glass and then into the water, that the straw changes and is suddenly over there. Now we know that the straw is straight. The straw is not bending or jogging, and it's just a trick of the light. And this is because the light that was originally moving not directly towards our eye, but farther away towards this side of the glass, is now being bent as it leaves the water, enters the glass, and then leaves the glass and enters the air. It's bending because the glass is curved. And that means that now the light is being directed towards our eye, which is not the direction that it was traveling before. So refraction is described by Snell's law, and that's shown here. We have n1, the index of refraction in the first medium, times sine of theta 1, which is the incident angle, incident to the surface between medium 1 and medium 2. That's equal to n2, this is the index of refraction in our second medium, times sine of theta 2, and this is the angle between the normal and the refracted ray in medium 2. So optical fibers are crucial for today's telecommunications industry and the internet. And this is because they're superior to copper wires in many ways. They're immune to electrical noise and interference. They transmit data at a higher rate. They can handle more simultaneous signals. So why are optical fibers so useful? And it all comes down to total internal reflection. So an optical fiber has an inner core made of a high refractive index transparent material like glass or plastic. So the core is the white portion in here. And then that core is encased in a lower refractive index transparent material called the cladding. The cladding is the gray portions there and here. And then that cladding is encased in some protective plastic jacket out here and down there. So let's examine a light ray that hits the wall of the core at angle theta I. This is the incident angle. As with any interface between two different media, part of the light may be reflected, and another part may be refracted at theta r, the refraction angle. So Snell's law tells us that n1 sine theta I is equal to n2 sine theta r, which we can then rearrange to give us sine theta r is equal to n1 over n2 times sine of theta I. Note that if n1 over n2, the ratio between our refractive indices, times sine of theta I is greater than 1, then there are no possible values for theta r that will satisfy because sine of x can't be any greater than 1. And this means that no light is refracted in such a case. Instead, all of that light is reflected. And this is called total internal reflection. So the largest possible angle of incidence, which still results in a refracted ray, is called the critical angle. So here we have an angle of 0. In that case, the light can go through. And as we increase the angle, at some point we get to a point at which now we can no longer get sine of theta to be greater than 1. And that means that all of the light instead has to be reflected. And none of it can be refracted. So none of the light can go this way. Because basically, as we increase the angle of incidence here, our angle of refraction is increasing faster because we're going from a high index of refraction material down here to a lower index of refraction material up there. And that means that at some point over here, we get to a point where this refraction angle is greater than 90 degrees. And that means that instead of coming out and going into our medium 2, our low refractive index medium, that light has to stay in medium 1, the medium that it was coming in from. So if n1 over n2, that ratio between our refractive indices, is greater than 1, then there is a range of angles at which total internal reflection occurs. So within a certain cone of acceptance then, all rays entering one end of the fiber will exit the other, because we have the light coming in, and as long as the light is within that angle, then that means that the angle of incidence there is over the critical angle. And so when that light strikes the interface between our core and our cladding, then none of that light is refracted, and instead all of that light is reflected, and that means it will bounce back and forth through here because the reflection angle will be the same going all the way down the fiber. And then any of that light coming in here has to go down and get emitted from the other end of the fiber, ignoring any losses. In reality, there will be small losses from absorption here. So if we place a chemically sensitive layer at the end of the fiber, then we can create an optode. And note that optode is a portmanteau of optical electrode. And we can deliver light to our sample from a light source via an optical fiber. We can then deliver light, transmitted, emitted, or reflected light, back from the sample to our spectrophotometer via an optical fiber. And that may be the same optical fiber, or it may be a different optical fiber. And if we use a CCD detector, then we have a spectrophotometer with no moving parts, aside from the flexible fiber optic cables. So we have over here a light source, and that light goes through this fiber optic cable. It goes to our sample cell here. The light passes through and is collected by another fiber optic cable, which then goes to the detector with our CCD array inside. And then that signal gets passed out to a computer. So we can use total internal reflection again for attenuated total reflectance. Instead of a cylindrical fiber, let's make a planar layer called a waveguide in which light is totally internally reflected. So we have down here this layer here in which our light is going in and it's being totally internally reflected, and then it comes out and goes to our detector. And if we then put a chemically sensitive layer, this is called the cladding, on the waveguide, then we will have a chemical sensor. So we put here, that's in green on my picture here, we put our cladding there, and even when light is totally internally reflected, that electric field penetrates some distance into the cladding. So you can see here, we've got the waveguide, and we've got our electric field oscillating back and forth, and total internal reflectance is occurring here at this interface. And out here we've got our cladding, but that electric field decays as we go into the cladding. It doesn't just immediately drop off to 0. And we can take advantage of the fact that it doesn't drop off to 0 here. The portion that penetrates then is called our evanescent wave. So that's this portion out there. So our electric field E is decaying exponentially with distance, and we see that here, where E naught is the magnitude of our electric field at the waveguide cladding interface. E is the electric field some distance away. X up there is the distance that we are moving into the cladding. Lambda is the wavelength of light in the vacuum, not in our media here. dP is the penetration depth. This is the distance at which the evanescent field decays to 1 over E of E naught. Now 1 over E is 37% of E naught. And so dP is shown over here and depends upon the wavelength of light in a vacuum, the index of refraction of our two media, and the incident angle. For example, with an index of refraction of medium 1 of 1.70 and an index of refraction in medium 2 of 1.45, then the critical angle is 58.5 degrees. And at 70 degrees incidence, then 590 nanometer light penetrates 140 nanometers. And this is more than enough to interact with many, many layers of large molecules like proteins, whose dimensions are around 10 nanometers. And we can now use this effect in an attenuated total reflectance IR sensor. And note that attenuated here means decreased. So we're looking at how much the light is being decreased by some chemicals on that cladding. So over here we've got a schematic for an attenuated total reflectance spectrometer. And we've got our diamond crystal that's sitting here. And again, we see it blown up down there. Our diamond crystal is acting like a waveguide, so we've got our infrared light coming in, being totally internally reflected a few times, and going out to our detector. And the top surface here is in contact with a liquid channel that's carved into a block of Teflon. So we've got a block of Teflon here, and we've got some liquid that is allowed to flow through. In our channel then, we've got some hydrophobic sorbent beads. And for the experiment depicted here, liquid soda is then pumped through the channel, caffeine adsorbs onto the surfaces of the beads, and this concentrates our caffeine. And then as infrared light passes through the diamond, then the evanescent wave interacts with the caffeine, and the wavelengths at which caffeine absorbs are attenuated. And so you can see here, the black trace there is 50 micrograms per milliliter of caffeine in water, analyzed using infrared spectrophotometry. But if we use attenuated total reflectance then, we're essentially concentrating that caffeine, and you can see now we have pumped through 3 milliliters of water containing our caffeine at the same concentration of 50 micrograms per milliliter, but now that caffeine has adsorbed onto the surface of those sorbent beads, and so now we have a much higher concentration of caffeine, and now we can get a much better signal-to-noise ratio using attenuated total reflectance. So now let's turn to surface plasmon resonance. When an electric field is applied to a metal, conduction electrons are basically free to move in response. So you can see here we've got some electrons here, and as the electric field points one direction and then the opposite direction, we've got our electrons moving one way and then the other. Now, a surface plasma wave, or a surface plasmon, is an electromagnetic wave that propagates along the interface between a metal and a dielectric, so an insulator. Now, the electromagnetic field decays exponentially into each layer, but it's concentrated in our dielectric layer. So you can see here in the metal layer, that electric field is relatively weak, but in the dielectric layer, that electric field is significantly stronger. And a surface plasmon resonance can take advantage of this, as shown here. So monochromatic light that's polarized in the plane of my board here is passed into our prism. So that's coming in here. And at the bottom of the prism here, we've got about 50 nanometers of gold. And then the bottom of the gold is coated with a layer that's 2 to 20 nanometers thick of a chemical that binds to our analyte. So at low theta, this is low angle of incidence, most, but not all, of our light is going to be reflected by the gold. And as theta increases to our critical angle for total internal reflection, then the reflectivity goes to 100%, at least ideally. So initially, at low angle of incidence, then most of our light is being reflected. And then as we increase our incident angle towards the critical angle, then that reflectance goes up. The reflectivity goes up to 100%, or near 100% at least. And now at this point, we now have total internal reflection occurring. And then as theta increases farther, then a surface plasmon, and again this is our oscillating electron cloud, is set up. And this absorbs energy from our incident light, and the percent reflectivity is dropping. And of course then our reflectivity is dropping below 100% here. Now the range of angles over which the plasmon is in resonance with our incident light is relatively narrow. We have a relatively narrow band here where that plasmon is interacting with the light. And thus there's a sharp decrease in the reflectivity versus angle curve. And as the angle increases farther, then the resonance lessens and the reflectivity goes back up. So that reflectivity minimum angle depends upon the refractive indices of all the layers involved. The angle changes by about 0.1 degrees when a thin polymer layer is applied to the gold. And then when analyte binds to the polymer, the refractive index changes slightly, and thus the angle at the reflectivity minimum changes slightly. Now commercial instruments can measure changes in angle of about 10 to the minus 4 to 10 to the minus 5 degrees. So they're incredibly precise. So that was optical sensors.